Section 1 Introduction. We're here to talk about the power and potential of transformer-based large language models, or LLMs for short. These models have shown impressive capabilities in in-context learning, ICL, making them a popular choice for many tasks in the field of natural language processing, NLP. One of the key features of these models is their self-attention mechanism, which allows for efficient, parallel training. This mechanism enables the processing of long sequences of data in a distributed way. However, there's a catch. The length of the sequences that an LLM can handle, known as its context window, directly impacts the amount of space available for providing examples. This, in turn, can limit the model's ability to learn in context. If the context window is too small, the model may not have enough examples to learn from, which can hinder its performance. This limitation can be particularly problematic for tasks like summarization. Another challenge with these models is their handling of positional information. In language, the position of words or tokens is crucial for understanding meaning. However, the self-attention mechanism of transformers doesn't directly encode this positional information due to its parallel nature. To address this, transformers use something called positional encoding. The original transformer models used a fixed sinusoidal position encoding, which was later improved to a learnable position encoding. More recently, relative positional encoding schemes have been developed, which have further improved the performance of transformers. Despite these advancements, one persistent issue with positional encodings is their inability to generalize beyond the context window seen during training. While some methods, like alibi, can do some generalization, none can handle sequences significantly longer than their pre-trained length. To overcome this limitation, we've proposed a few solutions. One of these is the NTK-aware interpolation, which takes into account the loss of high frequency. We've also proposed two improvements to this method: the dynamic NTK interpolation for pre-trained models without fine-tuning, and the NTK-by-part interpolation, which performs best when fine-tuned on a small amount of longer context data. We're thrilled to see that these methods have already been incorporated into open-source models like Code Llama and Qwen 7b. In this paper, we're not only going to discuss our previous work on these interpolations, but we're also going to introduce a new method called YaRN, yet another rope extension method. This method is designed to efficiently extend the context window of models trained with rotary position embeddings, ROP, including the Llama, GPT Neox, and PaLM families of models. After fine-tuning on a sample that's less than 0.1% the size of the original model's pre-training data, YaRN achieves state-of-the-art context window extension. Section Summary. Transformer-based large language models, LLMs, have become popular for natural language processing tasks due to their strong in-context learning abilities. However, the context window of these models limits their ability to perform in-context learning effectively. Positional encoding is used to address the lack of positional information in self-attention, but current methods struggle to generalize beyond the training context window. This paper introduces YaRN, a method that efficiently extends the context window of models trained with rotary position embeddings, ROP, achieving state-of-the-art results with fine-tuning on a small representative sample of the original model's pre-training data. Section 1.1 Acknowledgements. We'd like to express our gratitude to Stability AI, Carper AI, and Eleuther AI for their generous provision of substantial computing resources. These resources were instrumental in training our models and completing this research. We also want to extend our thanks to Jonathan To and Dakota Mayen for their guidance on using the Stability AI compute cluster. Additionally, we appreciate A16Z and Pygmalion AI for supplying resources to conduct evaluations and experiments on our models. Now, let's delve into the background and related work. Our research is primarily based on the rotary position embedding, ROP, concept. Imagine we have a sequence of input tokens, let's call them W1, W2, and so on, up to WL. We represent these tokens as embedding vectors, which we'll denote as X1, X2, and so on, up to XL. These vectors exist in a space that we'll call R to the power of D, where D is the dimension of the hidden states. In the attention layer, these embeddings, along with their position indices, are transformed into what we call the query and the key vectors. We'll denote the query vector as QM and the key vector as KN. These vectors exist in a space that we'll call R to the power of L, where L is the hidden dimension per head. Next, we calculate the attention score. This is done by taking the dot product of the query and key vectors, dividing it by the square root of D, and then applying the softmax function. In the rope, we make an assumption that D and L are even numbers. We then treat the embedding space and the hidden states as complex vector spaces. This allows us to calculate the dot product as the real part of the standard Hermitian inner product. To convert the embeddings into query and key vectors, we use R linear operators. These operators transform the embeddings into complex coordinates. The functions that perform this transformation are denoted as FQ and FK. The main advantage of this approach is that the dot product between the query vector and the key vector only depends on the relative distance between M and N. In real coordinates, the rope can be written as a matrix multiplication involving trigonometric functions like cosine and sine, and the query vector. This matrix multiplication is a function of the position index M and a parameter theta, which is a function of the dimension D. Section summary. The authors express their gratitude to Stability AI, Carper AI, Aluther AI, Jonathan Toe, Dakota Mayan, A16Z, and Pygmalion AI for their support in terms of computing resources, advice, and evaluation tools. The basis of their work is the rotary position embedding, ROPE, which involves converting input tokens into query and key vectors using complex vector spaces. By utilizing ROPE, the authors are able to calculate the attention score based on the Euclidean inner product of the query and key vectors. Section 2.2 Positional Interpolation. Let's delve into the concept of positional interpolation. When we use language models, they are typically pre-trained with a fixed context length. This leads us to wonder how we can increase this context length by fine-tuning the model with a smaller amount of data. For language models that use ROPE, or rotary positional embedding, a method called position interpolation, PI, was proposed to extend the context length beyond the pre-trained limit. The researchers found that directly extrapolating the position indices didn't work well for sequences longer than the pre-trained limit. However, they discovered that interpolating the position indices within the pre-trained limit, with a bit of fine-tuning, worked quite well. To explain this in simpler terms, they took a pre-trained language model with ROPE and tweaked the ROPE formula. This new formula allowed them to extend the context window beyond the pre-trained limit. They then fine-tuned the language model further using significantly fewer tokens, a few billion, and successfully extended the context window. Now, let's introduce some additional notation. We assume that the interpolation of the ROPE embeddings is symmetric in both the Q, K, and sin, cos domains. We can simplify this into a general form, where we introduce two new functions, G, M, and H, theta underscore D. For positional interpolation, we also introduce a scale factor, S, which is the ratio of the new context window to the old one. In the following sections, whenever we introduce a new interpolation method, we only need to specify these two functions, G, M, and H, theta underscore D. We also define a term called the wavelength of the ROPE embedding at a certain dimension. This wavelength describes the number of tokens needed for the ROPE embedding at a certain dimension to complete a full rotation. It's highest at the lowest dimension and lowest at the highest dimension. Some interpolation methods, like positional interpolation, don't consider the wavelength of the dimensions. We refer to these as blind interpolation methods. Others, like YaRN, do take the wavelength into account, and we classify these as targeted interpolation methods. Section summary. The authors propose a method called positional interpolation, PI, to extend the context length of language models beyond the pre-trained limit. By interpolating the position indices within the pre-trained limit and fine-tuning the model, they successfully achieve context window extension. They also introduce the concept of scale factor, S, as the ratio between the new context window, L, and the pre-trained limit, L, and define wavelength, lambda underscore D, as the length of tokens needed for a ROPE embedding dimension to perform a full rotation. Section 2.4 Related work. Our work builds upon the existing models that have been pre-trained with ROPE, with the goal of extending their context size. ReRope, a related project, also aims to do this and claims to achieve an infinite context length without the need for fine-tuning. This claim is supported by a consistent decrease in loss as the context length increases up to 16K on the Llama 213B model. However, ReRope achieves this by altering the attention mechanism, which means it's not purely an embedding interpolation method. As it's currently incompatible with flash attention 2 and requires 2 attention passes during inference, we don't include it in our comparison. At the same time as our work, LM Infinite proposed ideas similar to our project, YaRN, but with a focus on on-the-fly, length generalization for models that haven't been fine-tuned. Like ReRope, LM Infinite also modifies the attention mechanism of the models, making it incompatible with flash attention 2 and not purely an embedding interpolation method. Our methodology differs from pi, which stretches all rope dimensions equally. We found that this approach doesn't accurately predict the complex dynamics between rope and the internal embeddings of the language learning models, LLMs. In the following sections, we'll discuss the main issues we've identified with pi and how we've addressed them to develop our full YaRN method. One of the main issues we've identified is the loss of high-frequency information. From an information encoding perspective, it's been shown that deep neural networks struggle to learn high-frequency information if the input dimension is low and the corresponding embeddings lack high-frequency components. This is similar to the situation with rope, where a token's positional information is one-dimensional and expanded to an n-dimensional complex vector embedding by rope. When the rope embeddings are stretched indiscriminately, important high-frequency details can be lost. These details are necessary for the network to distinguish between tokens that are very similar and very close. We believe that this issue might be the reason for the slight increase in perplexity for short context sizes after fine-tuning on larger context sizes observed in pi. To address this issue, we developed the NTK-aware interpolation. Instead of scaling every dimension of rope equally, we distribute the interpolation pressure across multiple dimensions by scaling high frequencies less and low frequencies more. The simplest way to achieve this is to perform a base change on the value of theta. In our tests, this method was more effective at extending the context size of non-fine-tuned models compared to pi. However, it does have a major drawback. It's not just an interpolation scheme, and some dimensions are slightly extrapolated to out-of-bound values. This means that fine-tuning with NTK-aware interpolation yields inferior results to pi. Additionally, the theoretical scale factor S doesn't accurately describe the true context extension scale. In practice, the scale value S has to be set higher than the expected scale for a given context length extension. Just before we released this paper, Code Llama was released, which uses NTK-aware scaling by manually setting the base B to 1m. Section Summary. The related work section discusses two methods, rerope and LM-infinite, that aim to extend the context size of pre-trained models without fine-tuning. Rerope achieves this by modifying the attention mechanism, while LM-infinite focuses on on-the-fly length generalization. The methodology section introduces the NTK-aware interpolation method, which addresses the issue of losing high-frequency information when interpolating rope embeddings. This method spreads out the interpolation pressure across multiple dimensions by scaling high frequencies less and low frequencies more. However, it has the disadvantage of extrapolating some dimensions to out-of-bound values, resulting in inferior results compared to the traditional interpolation method. Section 3.2 Loss of Relative Local Distances, NTK-by-parts, Interpolation, Block NTK-parts. In this section, we delve into the concept of NTK-by-parts, interpolation, which is a fascinating aspect of rope embeddings. We've noticed that when we use a context size L, there are certain dimensions D where the wavelength is longer than the maximum context length observed during pre-training. In other words, the wavelength is greater than L. This implies that the embeddings of some dimensions might not be evenly distributed in the rotational domain. In the case of pi and NTK-aware interpolation, we treat all the rope hidden dimensions equally, meaning they all have the same impact on the network. However, our experiments have shown that the network treats some dimensions differently from others. As we've mentioned before, for a given context length L, the wavelengths of some dimensions are larger than or equal to L. We hypothesize that when the wavelength of a hidden dimension is larger than or equal to L, all pairs of positions encode a unique distance, suggesting that the absolute positional information is retained. However, when the wavelength is short, only the relative positional information is available to the network. When we scale all the rope dimensions either by a factor S or using a base change B', all tokens become closer to each other. This is because the dot product of two vectors rotated by a smaller amount is larger. This scaling significantly hampers a language model's ability to understand small and local relationships between its internal embeddings. We believe that such compression confuses the model about the positional order of nearby tokens, thereby negatively affecting the model's abilities. To address this issue, we've decided not to interpolate the higher frequency dimensions at all, based on our observations. Specifically, if the wavelength is much smaller than the context size L, we do not interpolate. If the wavelength is equal or larger than the context size L, we only interpolate and avoid any extrapolation. Dimensions in between can have a bit of both, similar to the NTK-aware interpolation. To find the dimension D we want given the number of full rotations R at a certain context length L, we can use the following equations. The wavelength of dimension d is equal to 2 pi times b raised to the power of 2d divided by the absolute value of d. The number of full rotations r is equal to L divided by the wavelength of dimension d. Solving for d, we get d equals the absolute value of d divided by 2 times the natural logarithm of b, times the natural logarithm of L divided by 2 pi times r. We also suggest that all dimensions d where r is less than a certain value alpha should be dimensions where we linearly interpolate by a scale s, and r greater than a certain value beta should not be interpolated at all. We define the ramp function gamma underscore d to be 0 if r is less than alpha, 1 if r is greater than beta, and the fraction of r minus alpha divided by beta minus alpha otherwise. With the help of the ramp function, we define the new wavelength as the sum of 1 minus gamma underscore d times s times the original wavelength and gamma underscore d times the original wavelength. The values of alpha and beta should be adjusted on a case-by-case basis. For instance, we found that for the llama family of models, good values for alpha and beta are 1 and 32, respectively. After converting the wavelength to theta, the method can be described as follows. G, m, equals m, and h, theta underscore d, equals the sum of 1 minus gamma underscore d, times theta underscore d divided by s and gamma underscore d times theta underscore d. Using the techniques described in this section, we've developed a variant of the method called NTK-by-parts, interpolation. This improved method outperforms the previous pi and NTK-aware, interpolation methods, both with non-fine-tuned models and with fine-tuned models. As this method avoids extrapolating the dimensions that have uneven distribution in the rotational domain, it avoids all of the fine-tuning issues from previous methods. Section summary. The rope embeddings in language models have some dimensions where the wavelength is longer than the maximum context length, indicating uneven distribution in the rotational domain. We found that the network treats some dimensions differently, with longer wavelengths retaining absolute positional information and shorter wavelengths only preserving relative positional information. Stretching all dimensions impairs the model's ability to understand local relationships, so we propose a new NTK-by-parts interpolation method that avoids extrapolating unevenly distributed dimensions, resulting in improved performance compared to previous methods. Section 3.3 Dynamic Scaling, Dynamic NTK, Interpolation, Mozilla Reddit. In this section, we'll discuss two key concepts: dynamic scaling and the increase in average minimum cosine similarity for long distances. Firstly, let's talk about dynamic scaling, which we also refer to as the dynamic NTK method. When we use rope interpolation methods to increase the context size without fine-tuning, we want the model to handle longer context sizes smoothly. We don't want the model's performance to drop drastically if the scale is set higher than necessary. Remember that in the pi, the scale s is the ratio of the new extended context length to the trained context length. In the dynamic NTK method, we adjust the scale s dynamically. If the ratio of the new context length to the trained context length is greater than 1, we set s to this ratio. Otherwise, we set s to 1. This dynamic adjustment of the scale allows all models to handle longer context sizes more gracefully. However, we need to be careful when using dynamic scaling with KV caching, as the rope embeddings are often cached in some implementations. The correct approach is to cache the KV embeddings before applying rope, as the rope embedding of each token changes when s changes. Next, let's discuss the increase in average minimum cosine similarity for long distances, which we refer to as YaRN. Even if we manage to handle local distances, we still need to interpolate larger distances at a certain threshold to avoid extrapolation. You might think this isn't a problem because global distances don't need to be very precise. The network just needs to know roughly whether the token is at the start, middle, or end of the sequence. However, we found that as the number of tokens increases, the average minimum distances become closer. This makes the attention softmax distribution more spiky, meaning it decreases the average entropy of the attention softmax. In simpler terms, as the effect of long-distance decay is reduced due to interpolation, the network pays more attention to more tokens. This shift in distribution causes a degradation in the outputs of the language model, which is independent of previous issues. Our goal is to reverse this decrease in entropy, or in other words, increase the temperature of the attention logits. We can do this by multiplying the intermediate attention matrix by a temperature greater than 1 before applying the softmax. But since rope embeddings are encoded as a rotation matrix, we can simply scale the length of the rope embeddings by a constant factor, the square root of the temperature. This length scaling trick allows us to avoid any changes to the attention code, which greatly simplifies integration into existing training and inference pipelines. However, it's difficult to compute an analytical solution for the temperature scale required with respect to the scale S, because our rope interpolation scheme interpolates rope dimensions unevenly. Fortunately, we've found experimentally that by minimizing perplexity, all llama models follow a similar curve. The square root of the temperature is approximately equal to 0.1 times the natural logarithm of the scale S plus 1. This equation was found by fitting the square root of the temperature where perplexity was lowest against the scale extension by a factor S, without fine-tuning, on various llama models. We've also found that this equation applies fairly well to llama 2 models, with only slight differences. This suggests that this property of increasing the entropy is common and generalizable across different models and training data. This final modification gives us our final YaRN method, which combines the methods described above and can be used during both training and inference. It surpasses all previous methods in both fine-tuned and non-fine-tuned scenarios and doesn't require any changes to the inference code. The only change needed is to the algorithm that initially generates the rope embeddings. The simplicity of YaRN allows it to be easily implemented in all inference and training libraries, including compatibility with flash attention. Section summary. In the dynamic NTK method, the scale used for rope interpolation is dynamically calculated based on the context size. This allows models to gracefully degrade when the context size is exceeded, instead of immediately breaking. Additionally, the YaRN method addresses the issue of decreased entropy in the attention softmax distribution caused by interpolating rope embeddings to longer context sizes. By scaling the length of the rope embeddings, the entropy can be increased, improving the performance of the language model. Section 3.5 Extrapolation and Transfer Learning. In our research, we utilized a dataset known as Code Llama, which contains 16,000 contexts. We adjusted the scale factor to approximately 88.6, which equates to a context size of 355,000. Interestingly, our network was able to extrapolate up to 100,000 contexts, even though it had never encountered these context sizes during training. Our approach, YaRN, is similar to other methods in that it allows for training with a scale factor larger than the dataset's length. However, due to computational limitations, we only tested a scale factor of 32. We achieved this by further fine-tuning a model with a scale factor of 16 for 200 steps, using the same 64,000 context dataset. Our results showed that the model with a scale factor of 32 could successfully extrapolate up to 128,000 contexts, even though it was only trained with 64,000 contexts. Unlike previous methods, YaRN is highly efficient at transfer learning when the scale factor is increased. This means that we were able to successfully transition from a scale factor of 16 to 32 without the network having to relearn the interpolated embeddings. This is because the model with a scale factor of 32 is equivalent to the model with a scale factor of 16 across all context sizes, even though it was only trained with a scale factor of 32 for 200 steps. In our experiments, we demonstrated that YaRN can successfully extend the context window of language model, LLM. Impressively, we achieved this result with only 400 training steps, which is about 0.1% of the model's original pre-training corpus. This represents a 10-fold reduction from previous methods and a 2.5-fold reduction in training steps, making YaRN highly efficient in terms of computation. To evaluate our models, we calculated the perplexity of long documents and scored them on established benchmarks. Our models outperformed all other context window extension methods. For training, we expanded the llama models with 2.7 billion and 13 billion parameters. We made no changes to the llama model architecture, except for the calculation of the embedding frequencies with scale factors of 16 and 32. We used a learning rate of 2 times 10 to the power of -5, with no weight decay and a linear warm-up of 20 steps. We also used Atom W with beta values of 0.9 and 0.95. For the scale factor of 16, we fine-tuned for 400 steps with a global batch size of 64 using PyTorch fully sharded data parallelism and flash attention 2 on the PG19 dataset. This dataset was divided into 64,000 segments, each beginning and ending with a specific token. For the scale factor of 32, we followed the same procedure, but started from the completed scale factor of 16 checkpoint and trained for an additional 200 steps. Section summary. The authors demonstrate that their model, YaRN, can successfully extrapolate and transfer learning to larger context sizes without the need to relearn interpolated embeddings. They achieve this with a significantly reduced number of training steps, making it computationally efficient. The resulting models outperform other methods in terms of perplexity and benchmark scores for context window extension. Section 4.2.1 Long Sequence Language Modeling. In this section, we'll be discussing our findings on long sequence language modeling and standardized benchmarks. We used two datasets, GovReport and ProofPile, to evaluate our model's performance on long sequence language modeling. These datasets are rich in long sequence samples, and we use their test splits for all our evaluations. To measure the model's performance, we used a method known as the sliding window with a window size of 256. We first looked at how the model performed as the context window increased. We picked 10 random samples from the ProofPile dataset, each with at least 128,000 tokens. We then calculated the perplexity, a measure of uncertainty, for each sample when truncated at 2,000 steps, ranging from a sequence length of 2,000 tokens to 128,000 tokens. We compared our results with other methods of extending the context window. Specifically, we looked at a publicly available Pi model trained at 32,000 from Together.ai and a model called NTK-by-parts, code Llama. We found that our model performed strongly across the entire context window, outperforming all other methods. One model that stood out was the YaRN model with a window size of 32. Despite the fine-tuning data being limited to 64,000 tokens, this model showed a continued decrease in perplexity up to 128,000 tokens. This suggests that our model can generalize to unseen context lengths. Next, we tested our model against standardized benchmarks using the Hugging Face OpenLLM leaderboard. This leaderboard compares various language models across 4 public benchmarks: the 25-shot ARC Challenge, the 10-shot Hella Swag, the 5-shot MMLU, and the 0-shot Truthful QA. We compared our model's performance with the established scores for the Llama 2 baselines, as well as publicly available Pi and NTK-by-parts models. We found that the performance difference between the YaRN models and their respective Llama 2 baselines was minimal. Moreover, there was an average drop in scores of just 0.49% between the YaRN models with window sizes of 16 and 32. This suggests that extending the context window from 64,000 to 128,000 tokens results in a negligible loss in performance. Section Summary. In the section 4.2.1 Long Sequence Language Modeling, the authors evaluated the performance of their model on long sequences using the GovReport and ProofPile datasets.